Okay, so this is 4.7. So putting it all together. Putting it all together. All right, so if we kind of take a step back, yes.
All right.
Go ahead.
Point to take a step back.
Yes. Go ahead.
When you solve for f double prime of x equal to 0,
Yes.
You don't know that that's an inflection point because you're not sure if it's it needs to switch from concave up to concave down.
It needs to switch, right? Yeah, and you're not sure if it switches.
And that's what the next part is to look for. You're looking for an alternation between positive and negative in between the values. Is that?
Yes, exactly. So there's a really yeah.
Sorry. So what's an example of something that could be 0 at a point and then be concave up on one side of it and then concave up on the other side of it? Like what would that be?
Good question. Yeah. Let's see. So can I give you a simple example?
Sure. I like simple.
Okay. All right. X to the fourth.
Oh, okay.
Because what's the second derivative?
Yeah.
12x squared, right?
Yeah.
So you have so you set it equal to 0, right? You get 0 for your pip, right?
Yep.
But then when you test, right? So you have 0 here. You test, say maybe -1, and then 1. What do you get for both? Positive. So that means concave up, and then it's concave up again. Right? So it's not an inflection point. So it was a possible inflection point, but it's not. It ends up not being an inflection point.
Okay.
But good question. Good question. All right. So let's see here. All right. So let's think through here all the stuff that we've done. And let's just kind of write down what we need, because we already know how to do everything. We just want to kind of put it all together in one place, and then we'll go through a bunch of examples. So what do we need to know? And the order of this doesn't matter that much, although the order that I'm going to write it is a pretty good one. So the first thing you really want to know, this is not really a calculus thing necessarily, and it's something that you often forget, but you want to make sure that you know the domain, because what starts happening is you can go through the motions and do all your steps, and then you can find maybe a critical point and then maybe a possible inflection point, but then you try to plug it in or plug in numbers around it, and all of a sudden it's not defined, and you start getting confused. You're like, oh, maybe I did something wrong. So you start spinning your wheel. So the first thing you want to do is figure out where your function is defined, so that if you find any critical points or anything like that outside of the domain, then just forget about it. Just throw them out. So there's no point worrying about something that's out of your domain. Does that make sense? Okay. All right. So, and then what else do you need? Well, you need to know the end behavior. So the end behavior is, so we haven't talked about this in a little while, but this is basically just means take the limit as x goes to infinity of your function, and the limit as x goes to minus infinity of your function. So what are some of the things that can happen here? If you get a number for one of those limits, what does that mean graphically? You have a horizontal asymptote, right? If you don't get a number, if you get infinity or minus infinity, then that means that your function just shoots off to positive infinity or negative infinity in some way, right? Okay, so that you need to know. Now, another thing that you need to know are any vertical asymptotes. And how do you typically find those? Where do you look for vertical asymptotes? the most common for sure is when the denominator equals 0. That's the most common. Another one that sometimes you forget is log functions, right? They have vertical asymptotes at 0, right? Because it shoots off to minus infinity there. Well, tangent, yes. I'll just put some trig functions. I mean, technically, you can put those under the denominator equaling 0, because tangent is sine over cosine, so whenever cosine equals 0, that's where you have the vertical asymptotes. But tangent has vertical asymptotes, right? Secant and cosecant have vertical asymptotes, and then cotangent, obviously, too, has vertical asymptotes. Okay, so you need to find those. Okay, now what else do we need? We need the intervals of increase and decrease. And what do I use to find those? Well, actually, hold on. Intervals of increase and decrease and local extrema. So these go together, so might as well put them in the same boat. But how do I find those? First derivative test with the number line and all that, right? Now, I typically don't advise doing the second derivative test in these because you're already finding the intervals of increase and decrease anyways. So if you already have that, well, then there's no point doing the second derivative test. That would be extra work. So, but if you feel like doing it, that's fine. Okay, and then the last thing is the intervals of concavity and inflection points. All right, so how do I find that? Not to be confused with the second derivative test, right? Okay, so there isn't really a name for it, but pips and all that stuff we just did. Okay. All right. So that's it. That's all we need. That's it. That's only that. Okay. So let's do one here. How about let's do cube root 3 cosine x plus sine x. Oh, sorry, square root. I saw that 3 and I said cube. Yeah, square root of 3 cosine x plus sine x. Okay. All right, so off we go. So what's the domain? So all real numbers, right? So all real numbers. Okay, I'll just kind of put that there. Okay, so that's fine. So when we say end behavior, we're really looking for, basically we're looking for horizontal asymptotes for the most part. So if it's obvious that there are none, you don't really need to do much. So this is the sum of sine and cosine. So if you just think of taking the limit as x goes to infinity, what do you know already? What is? What is that? Yeah, this does not exist, right? It just oscillates. So oscillates. Okay, so we'll forget about that. So some of these don't take much time. What about vertical asymptotes? So think of sine and cosine. Do those generally have no, right? You don't have a denominator, so no vertical asymptotes. See, we already did more than half of it. More than half of the steps there. Okay, so this is where it gets time consuming. 4. So intervals of increase and decrease and local extrema. So this is what we did last time, right? So what should we do?
Find the
First derivative, critical points, number line, test points, right? Okay, so let's do that. So what is the first derivative? Negative.
Root 3 sine x plus cosine x.
There we go. See, you can't drop the class.
What about the root 3?
Yeah, root 3 is a constant, right?
Yeah.
Okay, all right, so minus root 3 sine x plus cosine x. Okay, are there any points where the derivative does not exist? No. Okay. So let's set it equal to 0. So minus root 3 sine x plus cosine x equal to 0. Okay, so we have a trig equation here. So let's see. Any ideas? Well, not really, because there aren't any squared. Most of your identities are with sine squared and cosine squared. So, but moving, let's move root 3 sine x to the other side. So now what? Okay, divide both sides by sine x. So you can do cosine x divided by sine x equals to root 3. Yes or no? Is that okay? Okay, so this looks kind of bad, but it's actually not that bad, because so there's a couple ways you can think about it. You could think about it as cotangent. Where does at which angle does cotangent of x equal to root 3, right? That's one way of thinking of it. But you can also think of it like this. You can say, okay, well, let me go up here. So if I think of, so to get root 3, let's say you think about it one step back. You would have, say, divided cosine of that angle divided by sine of that angle, right? And all the angles that we know, what are they always divided by? They're always divided by 2, right? So if I have root 3 here, and I kind of think of this as a fill-in-the-blank problem, okay, what number goes under both fractions? It would be a 2, right? So here I didn't actually do anything, right? I just rewrote root 3 as root 3 over 2 divided by 1/2, right? Now, I don't really gain that much from it, except from maybe being able to say, well, what's the angle where cosine is root 3 over 2 and sine is 1/2? See how much quicker it comes than the other one? Right? So if you're thinking of, oh, which angle is cotangent root 3? It's like, I don't know, let me think. Cotangent, I never find that, right? But then when I ask, where's cosine root 3 over 2? Well, that comes out right away, because it's one of the common ones that you know, right? So, all right. So what did you guys tell me? Pi over 6. Okay. But that's not the only one, right? So you have to be a little bit careful. So let me okay, so pi over 6 is the most obvious one, but
Should do negative and negative.
7 pi 6 or 7 pi 6 started with 7 pi 6.
so we have this, right? Here's pi over 6, right? Okay, so that's quadrant 1. What other quadrants am I looking at? Where else is code? Quadrant 3, right? Because they're both negative. They're both negative, so then when you divide them, they're going to end up being positive, right? So, and you want the reference angle to be pi over 6 still, so what angle is that? 7 pi over 6. Okay, so, and then where's the next one? And it keeps going that way, right? Does that make sense? So you just keep adding, notice they're pi away from each other, right? So if you add pi or subtract pi from each of them, then you get to another point. So, okay. All right, so now, let's see here. So let's do our testing here. So I have pi over 6. I have 7 pi over 6. So what did you guys tell me the next one is? 13 pi over 6. Okay, sure. What about before pi over 6? This one right here. Not negative pi over 6, because that's in quadrant 4. Negative 5 pi over 6, right? Okay. All right, so now, what are some good test points? So remember, think easy numbers to evaluate trig functions at. So less than minus 5 pi over 6, what would be a really easy one? Negative pi, good. What about between minus 5 pi over 6 and pi over 6? 0. Okay. Pi. Next one. 2 pi.
Why are we looking at 4 points? Because really don't we just need to look at 3 points to look at the full period?
That is correct. But I just picked more just for fun. But yeah, you're right. You don't need that many. Yeah, the main thing you want to make sure is you want to make sure you have one full cycle. So what's the period of, it's going to be 2 pi again, right?
Period of
Of well, in this case, we're looking at the first derivative. So, I mean, the period's the same, but it's going to be 2 pi regardless, right? Does that make sense? So we don't really need all of them.
Are you looking at the period of the first function or the second function?
For
Concavities has to look at the second function. Or, I'm sorry, the
I'm looking at the first derivative right now in red.
okay,
The one I circled in red.
I'm looking at the second function.
Right? So the first, yeah, so I mean, they're both 2 pi, so it doesn't really matter, but and another thing to note here is that, so this is just the sum of sine and cosine. So notice that 0, 2 pi, these are the same, right? And so is, let's see here, minus pi, pi, and 3 pi, those are also the same. Right? When you plug in those values, you get exactly the same thing. So, right, because sine at all of these is going to be 0, right? So then, so when you plug it in, so f prime at, say, 0, what would you get? I'll write it down just for completeness here. But cosine of 0, which is 1, right? So it's going to be, so it's positive here, right? And what does that tell me again? That it's going to be increasing, right? Okay. And then, so we already said this is going to be the same as this one, right? So it's going to be positive at 2 pi, so it's going to be increasing there. And then if I plug in minus pi, we get minus root 3 sine of minus pi plus cosine of minus pi, which is, that's negative 1, right? So it's going to be negative here, and negative here. So there it's going to be decreasing. Okay, so what did we find? So let's say we're going to write it down here. Let's see, where can I write it down? Okay, so we can say that it's increasing on what intervals? From minus 5 pi over 6 to pi over 6, right? Okay, and then union. Where's the next interval of increase? To 13 pi over 6. Union, and then dot, dot, dot. So it just keeps going, right? And then what about the interval of decrease? So same thing, right? Except that this time it would be decreasing from pi over 6 to 7 pi over 6. Why don't I do this? Let me erase this, and I'll write it down right here. So it's going to be decreasing. Let's see, pi over 6 to 7 pi over 6, right? And then 13 pi over 6 to, where's the next one? How many? 19 pi over 6? Yeah, we just add pi, right? And then dot, dot, dot. And then technically you would do the union dot, dot, dot this way as well, to the left side. But okay, and then also, let's see, let's do, okay. We found local maximums and local minimums, right? So where's the local maximum? Let's just write down the x value because we don't really have room for the y value here. But, oh, that's not a good color, is it? Let's see. I'll do this dark blue. Okay, so which one of these is a local max? So I have pi over 6, right? And then where's the next one? Well, that's a minimum. So 13 pi over 6. So how do I get from pi over 6 to 13 pi over 6? Add, not pi, 2 pi, right? So a couple different ways you can write it. You can write it as pi over 6 plus or minus 2k pi. Or what's another way we could write that? About 12k plus 1 pi over 6. Is that the same thing? Where k is an integer? It's the same, right? How do I get 12k plus 1 pi over 6? Yeah, I just take what we just wrote down, right? If you just get the common denominator here, which is 6, multiply top and bottom by 6, then you can just put them together, right? Okay. And then where are the local minimums? So the same thing, right? So 7 pi over 6, let's say, plus or minus 2k pi. How would you write that one in closed form? Nope. 12k plus 7 pi, right? Over 6,
Oh, yeah.
right? Because you just combine, it's just common denominator and then combining them into 1, right? So 12k plus 7 pi, all over 6.
I got lost. Why does it go from pi over 6 plus minus 2 pi over 1 equals 12k plus 1?
So here, let me erase this a little bit. Which one? The max or the min?
Both. You know how it goes to 12k plus 1 pi?
Let's see. Yeah, so if you just take this one and you multiply top and bottom by 6,
Oh, okay.
right? So that's basically, I mean, that's all it is. So then the other one, 7 pi over 6, plus or minus 2k pi, which is 12k plus 7 pi over 6. And again, where k is an integer, right? Yeah? So far so good? Now notice, are we done? No, we're not even, well, we are close, actually. Okay, so we have, right, so here we have, let's maybe box this up here. So these are the intervals of decrease, intervals of increase. Here's the local maximums and minimums. And again, I'll reiterate, very important when you're doing this, when you're finding the maximums and minimums, make sure that the function's defined there. Because if it isn't, well then it's not really a maximum or a minimum. Because you could have a direction change and have it not be a max or a min. So, but how do I know that these actually are maximums and minimums, even without finding the y value? Yeah, because the very first thing we did was find the domain, right? And we said, oh, well, it's defined for all real numbers, so they're definitely going to be maximums. Okay, let's go open up a new page here. So let's see. So this is my first derivative, right? So we're going to get the second derivative. So what would that be?
Step 5.
Yep. So step 5. So second derivative is going to be
Root 3 cosine x minus sin x.
root 3 cosine x minus sine x. Is it positive root 3 cosine x or negative?
Positive.
Okay. Sure?
So isn't that minus belongs to sine, or did you?
It's negative. Because what's the derivative of sine? Positive cosine, right? So what happens with this negative? That's right.
It stays.
It's part of the constant, right?
Yeah.
Okay. Okay, so now if I would have kept that mistake, would that have messed up my answer?
Yes.
Yep. Yeah. So you got to be careful. Okay, all right. Let's see. So this we just did, right? So let's find our pips. So you set them equal to set it equal to 0, right? So set this equal to 0. Let's see. Let's say I move sine x to the right side, maybe. And then maybe divide by cosine x. So similar to what we did for the other one, but the angle is different, right? So what would be the angle where sine x over cosine x is minus square root of 3? Which one?
556. Oh wait, no.
Mm-mm. So think of it the same way like we did the other one. So think of it as not minus root 3, but minus root 3 over 2 over 1/2. So what quadrants is that? So it's negative, right? So what quadrants would we be looking at?
4 and 2.
Yeah, 2 and 4, right? So here we're looking at 2 and 4 because we're looking for the quadrants where sine and cosine are different. And then what's the reference angle that we're looking at? Pi over 3, pi over 4, or pi over 6?
Pi over 3. That'd be 4 5/3.
So pi over 3, right? Because we want sine to be the larger one, so it's going to be up here, right? Sine of pi over 3 is root 3 over 2, right? That's the reference angle we want. So, but it's not in the first quadrant, right? So the reference angle is pi over 3. So then what angle would it be in the second and the fourth quadrant?
2 pi thirds and 5 pi.
2 pi over 3 and then 5 pi over 3, right? So basically it's 2 pi over 3. Well, let's generalize it. 2 pi over 3 plus or minus k pi, right? You just keep adding or subtracting pi to get to the next one. Okay. So does that make sense for that? Yeah? Any questions up to this point? Or okay. So then next thing is what we just did, right? So 2 pi over 3, 5 pi over 3. Let's see. Let's put a couple more here. So what would be the next one after 5 pi over 3? 8 pi over 3, right? Just keep adding pi or subtracting pi. So left of 2 pi over 3, what would that be? Negative pi over 3. Yep. Okay, so what would be some good test points here? Zero there, right? Okay. All right, what else?
Pi over 2.
3 pi over 2. You mean between 2 pi over 3 and 5 pi over 3?
Yes.
Sure, we could do that. What about between 5 pi over 3 and 8 pi over 3? 2 pi works, sure. What about after 8 pi over 3? How about 10 pi over 3? Would that be good? Or 9 pi over 3 is even better, no? What's 9 pi over 3? That's 3 pi, right? Let's see. And then less than minus pi over 3? Negative. Would negative pi work, or is that too far? Negative pi over 2 would be fine. But negative pi over 3 is okay too, right? Because, so think about it. This is minus pi over 3 right here. How far is it until the next one? It's not until this angle right here, right? So negative pi would still be okay. Does that make sense? So actually this 3 pi over 2, that would be fine, but pi would also be okay. So, yes?
So would it at this point make sense to double check that those values exist?
For the function? Not for this problem, because we already found the domain, and the domain is all real numbers.
Oh, okay.
So we don't have to worry about it. Yeah. Any other questions before we continue here? Okay. So now, so where am I going to plug all this into? Second derivative.
Are we gonna have a shortcut like the first one where
Why is it that we do, yeah. But why is it that we have, well, why are we plugging it into the second derivative? Because we're looking for concavity, right? So it's depending on what you're looking for, that tells you what function you plug it into, right? So minus pi, what is that the same as? The same as the value at 3 pi, no? Any other ones? So what is the second derivative at negative pi or 3 pi? So cosine of 3 pi, that is negative 1, right? So this is going to be positive root 3, so positive, right? So positive, positive, so that means it's going to be concave up there, right? Concave up, concave up. And then what about, let's see, 0 and 2 pi, that's the same, right? Those are both going to be the same. So what is that? Minus root 3 of cosine of 0, which is minus root 3. Notice I'm not even writing sine down. Why not? Because sine of 0 or 2 pi or minus pi or 3 pi is always going to be 0, right? So that's why I didn't write it. It's not because it shouldn't be there. It's just I'm short on space, so I just didn't put it in there. Okay, so it's going to be minus, minus, so it's going to be concave down, right? And then last but not least, if I plug in 3 pi over 2, I get minus sine of 3 pi over 2, right? Because cosine of 3 pi over 2 is 0 this time. And that's going to be positive 1, right? Because, yeah, it's minus 1, but then you have the minus in front, so it's going to be plus 1. All right, so do we have any inflection points? We definitely do, right? So we have inflection points. Let's see here. So where are my inflection points? At x equals to negative pi over 3, 2 pi over 3, 5 pi over 3, dot, 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 right? How would I write that in closed form? So another couple different ways you can write it. You can also write it as 2 pi. So you pick one to start off at, right? 2 pi over 3, let's say. And then you add what? Yeah. So you just keep adding pi. That's how often you have the inflection points, right? So if you're at an inflection point, if you add pi to it, you get to another inflection point. Or subtract, right? Well, if k is an integer, then it's built in, right? Because the integers are positive or negative. So, and if you simplify that, you get, what would I get? 3k plus 2, right? Times pi divided by 3. And if I wanted to know the y values of those inflection points, what would I do? Plug them into the original function, right? Does that make sense? Okay, so any questions with all this stuff? Are we ready to sketch the graph? Sure, might as well, right? Okay, so Okay, so since most of our information is here, oh no, I can't do it. Okay, all right. Well, let's just take note of our information here. So a couple different things. So the domain, all real numbers, right? And behavior, we said no horizontal asymptotes. We said there was no vertical asymptotes. And we have the local extrema here and the intervals of increase and decrease here, right? So, and then we have the inflection points right here. Whoa, wowzers. Okay, and then we have, I don't know what happened there, but the intervals of concavity right here, right? Okay, so let's do a new, oh my gosh, what just happened? Write down, what's our info that we found out?
Where it's increasing and decreasing.
Well, maybe, why don't we do this? Let's draw an axis. And I won't rewrite the info again because you guys have it on your thing. But, okay, so why don't you guys give me, let's see. Where's the first local maximum? 5 pi over 6? Or pi over 6? Pi over 6, okay. So let's say pi over 6. And so here's local max, right? And so that's at x equals pi over 6. And then what would y equal to there? 2? So if you plug it into the original function, you get 2. Is that right? So the original is this function, root 3 cosine x plus sine x. So let me write that down. So root 3 cosine x plus sine x. Okay, so cosine of pi over 6. So root 3 times root 3 over 2 plus 1/2. So then you get 2, right? Yeah, okay. And then where's the, there's a minimum over here, right? Where was that? 7 pi over 6? 2, 3, 4, 5, 6. Okay, 7 pi over 6. All right, so here there's a minimum. And where was that? What's the y value? If I plug in 7 pi over 6, I get -2. All right. So right here. Okay, and then what about left of? So where's the next minimum to the left of pi over 6? Where was that? No, left of pi over 6. -5 pi over 6, right? So then it would be about right here. Okay, so let's just keep it to that. So from -5 pi over 6 to pi over 6, we said it's increasing, right? And then from pi over 6 to 7 pi over 6, we found that it's decreasing. And then increasing after that. And then over here to the left, it was decreasing. Is that what we found? Yeah. Good, right? Okay, now what about the concavity? So we found an inflection point where? What's pi over 3? Okay, so right about here, roughly, is pi over 3. And what's the y value at pi over 3?
It was -pi. It was -pi over 3 or 2 pi over 3. Yeah.
So let's see, where are we? Oh, right here. Oh, 2 pi over 3, okay. Yeah. So I'll erase that. It happened again. Whenever I go back and then go. Can't make any mistakes. Let's see. So 2 pi over 3 is closer to here. 2 pi over 3. Okay. So there's an inflection point right here, right? And what's the y value at 2 pi over 3? So if I plug in 2 pi over 3 into the function, I would get 0? Yeah? Yeah? What is it? Root 3. What's cosine of 2 pi over 3? Well, it's minus 1/2, right? Okay. And then plus sine of 2 pi over 3 is positive root 3. Okay. So it is 0. Yeah. Okay. So then the inflection point is right here, right? So, okay. Where's the next inflection point after 2 pi over 3? 5 pi over 3, right? So roughly right around here. So 5 pi over 3. Now, what's the concavity between those two? So from 2 pi over 3 to 5 pi over 3, what did we find for the concavity? Concave up. Okay. And then well, now I'm off scale here quite a bit, aren't I? Because my next inflection point to the left would be at negative pi over 3. So here it's concave down, right? And then concave up. And then concave down. 2, 3, 4. Maybe I'll just move this one a little bit. It's a bit. I'm going to move it a little bit to the left. Maybe like right there. Okay. All right. That's a rough sketch. So, all right. So that looks like probably a good amount of information to do a pretty good sketch. So let's see. At minus 5 pi over 6, this was a minimum, right? Wasn't it? And it was minus 2 there, right? Is that? Yeah. Okay. So notice how we have several points, right? So we know it passes through right here, minus 5 pi over 6, minus 2. The inflection points, it's equal to 0. Then we have this max. Then we have 0 again, the minimum, and then 0 at the inflection point. And then you just kind of put the information together, right? So here, it's going to be increasing and concave up. And what happens at the inflection point? It's still increasing, right? But then it's going to be concave down. And then here, what happens? Changes from increasing to decreasing, right? But the concavity is still the same, so then it goes down like that. And then what happens at this point? It's still decreasing, right? But now it's concave up. And then here it's increasing, but still concave up. And then it'll increase concave down, and then just keeps going that way, like that. Yeah? Okay, so none of those steps in isolation are difficult, right? The difficult thing is getting everything right first time around. And the time that it took, I mean, how long did that take us? Close to 40 minutes. That was one problem, and this wasn't even that hard of one. We found no horizontal, notice we skipped. We didn't have any horizontal asymptotes, no vertical asymptotes. The domain, we didn't have to do anything. I mean, it was periodic, so that kind of makes it a little bit more work, but yeah. All right, so what did you guys find? What's the domain? All real numbers. So in this case, so since it's a natural log, you basically just set x squared plus 1 is greater than 0, but it's always greater than 0. So then the domain is all real numbers. What are the horizontal asymptotes? None, right? So you take the limit as x goes to infinity, and what do you get? You get infinity, right? So, okay. And then what about if I change this to minus infinity? Same thing, right? Okay. What about vertical asymptotes? None, right? So normally, so when you first see ln of x squared plus 1, what you think of is you say, okay, well, I know the natural log function has a vertical asymptote at 0, or when the argument is 0, right? So what you would do is you would say, okay, well, when it does x squared plus 1 equals 0, and then at this point you realize, well, you can't solve that, right? There's no real number, so none. But that's kind of the thought process that you want to go through anyways. Does that make sense? Okay. All right, so what's next? Yeah, all that jazz, right? So, okay, so let's find the derivative. So what's the derivative? 1 over x squared plus 1 times 2x, right? Okay. So, so what are the critical points? 0. And does the denominator give me any critical points? No, right? Because it can't ever equal 0. So this is the one and only critical point. Okay, so that's nice. So I'll do my number line, right? What are some good test points? Okay, and where am I going to plug these into? The first derivative, that's right. Okay, so the first derivative. Why am I plugging it into the first derivative? Trying to find if the function's increasing or decreasing, right? So, okay, so I have 2 times minus 1 divided by minus 1 squared plus 1, right? So it's negative, right? So that means that my function's going to be decreasing, right? So you can either put an arrow like that, or it's also common to put decreasing like that, maybe. Either way is fine. Okay, and then when you plug in 1, you get positive, right? So positive, so that means that it's going to be increasing. Okay, now at this point, am I 100% sure that I have a local something? Local minimum. Am I sure 100%? No. You should be. Yes. Why should you be sure at this point? Because the domain is all real numbers, right? So if this critical point was a point that was not in the domain, well then, yeah, right? You would say, oh, well, yeah, not sure, right? Well, yeah, obviously it wouldn't be, but but since the domain is all real numbers and you found a critical point and then it's decreasing, then it's increasing, then it's for sure going to be a minimum because your function's defined there. If it wasn't defined there, if there was some kind of a jump or a vertical asymptote, something like that, then it would not be a minimum. Does that make sense? Okay. All right. So, where's my local minimum? It's at 0. 0. That's right. Where do I get this second 0 from? So this 0 came from y, which is f of 0, which is ln of 0 squared plus 1, and ln of 1 is 0. So that's where I came from, right? Okay. All right. Good job. Good job, team. So any questions with that? Let's see. No, yeah, we should write it. Let's see. What I'm trying to do is to write it so that I have enough space to do the whole problem on this sheet of paper. So I'm going to do local minimum here. Okay, and then where is it increasing? 0 to infinity. And then where is it decreasing? Negative infinity to 0. So this just comes from the number line, right? This number line right here, where I did my tests. All right, so questions? So what comes next? Oh, yes, go ahead. Because it's where the I set the derivative equal to 0. Yeah. So you look for where it's equal to 0 and does not exist. So there are no points where it does not exist because the denominator can't equal 0. And then, but when x equals 0, then the whole derivative equals 0. Any other questions? Nope. Okay. So what's next? Second derivative. Okay. So let's see here. Oh, wait. Second derivative. So what is the second derivative?
2 over x squared plus 1.
X squared plus 1 times.
Does it simplify to that?
Yes.
Oh, well, okay. All right, so let's write it down, though. So it's going to be, so the derivative of the top, right, times the bottom. So 2 times x squared plus 1. And then minus 2x times the derivative of x squared plus 1, which is 2x, right? Divided by x squared plus 1 quantity squared. So what is that equal to? That's 2x squared plus 2 minus 4x squared. So what is that?
2x plus 2.
Negative 2x squared and then plus 2, right? So far so good or no? Okay. And then over x squared plus 1 quantity squared. And is that something I can simplify? So what is that? That's 2, and then if I factor out a 2, I'll get negative x squared plus 1, or 1 minus x squared. Okay. So if I factor out a minus 2, I'll get x squared plus 1, or, well, no.
No, you'd get minus 1.
So it ends up being a difference of squares, right? Yes or no? Okay. And then what about the bottom? So now what? Now what? How can I simplify that? What do you say?
I say we leave it.
I say we leave it. That is an excellent choice. Excellent choice. There's nothing you can do. So don't let your I call it mad slashing when you start going like this. When you just really want to slash something, get rid of stuff. So you just start crossing things out. It's like, oh, this is gone. It simplifies. Okay, but you can't simplify, right? Because you can't factor x squared plus 1. You can do nothing. Okay, so that's all right. It's no big deal. So this is the second derivative. All right, so what are my pips? So it's already factored, right? So minus 1 and plus 1 are my picks just from the numerator, right? So you set the whole thing equal to 0, and then whenever x is minus 1 or plus 1, the whole thing's going to equal to 0, right? Do I get any pips from the denominator? No, because again, it can't equal 0, right? So, okay. Now, what do I do with those guys?
Come on, number line.
Do the number line thing again, right? So, -1, +1. So what would be some good test points? 0, 2, -2. And where am I going to plug these into?
Second derivative.
Sure?
Yeah.
Okay, good. All right. Nice. Second derivative. Why? Because I'm looking for the concavity, right? And the second derivative tells me the concavity. All right, so if I plug in, so again, notice the denominator is always going to be positive, right? So I'm not even going to worry about the denominator. So I'm just going to put a star, ignore denominator. Since it's always positive, right? So, okay, so what do I have? I have -2 times, if I plug in -2, I'm going to get -2 times -1, right? Times -3. What is that? Negative. Okay. So what does that tell me? Concave down, right? Okay. If I plug in 0, I get -2 times 1 times -1, which is positive, right? So that means it's going to be concave up. And if I plug in 2, I get negative. So then it's going to be concave down. Okay, so do I have any inflection points? I do, right? So let's see. So inflection points. What are my inflection points? -1. 1 is the x value, and then what's the y value? ln of 2 and ln of 2. Where do I get that? Playing it into the original function, right? Okay, and then the intervals of concavity, I don't really have room for them, but you can write them down, right? So it's basically that. Okay, so can we draw a good sketch of this graph, you guys think? I think we can. All right, let's do it. Let's do it. Ln of x squared plus 1. Okay, so I'm just going to ask you guys to remind me here. So where's my maximum?
No maximum.
Okay, where's my minimum? 0, 0. Okay, so there's my minimum. And okay, so then that means that it's going to be increasing here, right? And then decreasing over here, right? Those were our intervals of increase and decrease. Okay, then we have concavity. So where's my inflection point? At 1 and -1, right? And ln of 2, what is that about? Is that, well, is it greater than 0 or less than 0? You sure? Okay, just making sure. It is greater than 0. Because it's 0 at 1, right? So then it would have to be after. The normal natural log function. So that's what I mean. Okay, so here I have inflection point, and then here I have an inflection point. Okay, so then let's write down. So what's the concavity between -1 and 1? What's the concavity? Concave up. And then after 1, it's going to be concave down, right? And then before -1, it's also going to be concave down. Is that what we found? Okay. So is that enough information to put together the graph? It should be, right? Because No horizontal asymptotes, right? Is that what we found? Yes. Good. Any vertical asymptotes? No. Then the domain is all real numbers, so then let's just put it together. So we have concave up, increasing, right? And then here, it's still increasing, but it becomes concave down, right? So it looks like that. And then if we go left of 0, it's concave up, decreasing, concave down, decreasing. That's a terrible job there. Let me redo that. It's not bad, I think. All right. Is that right?
Yeah.
We did it wrong. No. Just kidding. Just kidding. Oh, they always want you to go pro. Why are we even bothering with Wolfram? Desmos. All about Desmos. All right. But there it is, right? So right about 1, the concavity changes, and then notice it kind of looks like there's a horizontal asymptote, but is there? No. It's just the rate at which it's increasing just keeps getting smaller and smaller, but it still goes to infinity. All right, so questions? What is it? What about? Oh, it's x squared plus 1. No, it is plus 1. It looks like a minus 1 on the projector. But it is a plus. Look. Okay. Projector mode. Okay, questions? No? You guys are okay? I mean, I know you guys are not okay, but all things considered. Yeah, you just need to practice. That's right. That's exactly the right attitude. All right, do you guys need another example? Okay. All right, let's do another one. So we did log. Let's see. All right, what'd you guys get for the domain? What'd you get? But there's more than that. So it can't equal 0 because the denominator can't equal 0, right? But it has to be positive, right? Because it's the you have a square root in there, right? So x has to be strictly greater than 0. So if you only had the radical, it would be greater than or equal to. But because you also have an x on the denominator, it can't equal 0 either. So it's x has to be strictly greater than 0. Yeah? Okay. All right. What about vertical asymptotes? X equals 0, right? Because the denominator equals to 0. And the numerator is a constant, right? So if you take the limit as x approaches 0 from the left and the right, you will find that it very likely goes to infinity or negative infinity, right? Okay, so when the denominator equals to 0, it's kind of like you suspect that there's a vertical asymptote, but it's not 100% guaranteed. You should probably still find the limit from each side. Okay, now what about the horizontal asymptote? So you find the limit, right, as x goes to infinity. So you guys went through the steps here, right? So you guys probably divided by x, top and bottom, right? Okay. So if you do that, you get... Well, the limit as x goes to infinity, you have 8 times, so this is 1 over root x, right? That's what that reduces to, yes? Okay. Minus 1 over x, and then all divided by 1, yes? Okay, so as x goes to infinity, let's see here.
Why did you do it to the x? Why did you do it to the 8? 8 over x.
Because the 8 is outside of the parentheses. If it makes you feel better, you could do this.
Oh, if you just distribute it.
We could take it out of the whole limit. Because you can't divide, so if I did this, this would be completely incorrect. Because at that point, I'm basically dividing the top by x squared and the bottom by x. So you definitely don't want to do that. So then what's this? What's the limit as x goes to infinity of?
0.
That goes to 0, right? What about this guy?
0.
Also 0. So you have 8 times 0 divided by the number 1, right? Which is 0. Right? So it's a little challenging because it's been a while, right? Since we did limits. But they came back. They made a comeback. Okay. Now, I don't know if I would do the whole thing all over again for minus infinity. Kind of depends. But if I change this to a minus infinity, would that change anything?
Yeah, I would change the.
It's going to be the same thing, right? So it doesn't matter if it's positive infinity or negative infinity. You're still going to get 0 divided by 1. So it's 0. So what does that mean? That means that there's a horizontal asymptote at y equals 0, right? So that's what this means. Okay, so we have this, this, and this. That important information, right? In the red boxes. Okay, so any questions up to this point? You doing okay? Okay, so now what should we do next? First derivative. Okay, so first derivative, f prime of x equals to what do you guys want to do? Quotient rule, move the x up and do product rule. What did you guys do? You guys did quotient? Okay, fine, sure, good. Okay, so what is that? So I'm going to have 8, right? What's the derivative of root x minus 1? 1 over 2 root x. Okay, good. And then times x, right? Minus 8 root x minus 1 times the derivative of x, which is 1, and then all divided by x squared. Okay. Now this looks bad, but it actually simplifies a little bit, right? Because we have root x and x. What does that simplify to?
1 over 2 root x.
Well, root x on top, though, right?
Yeah.
And then the 8 and the 2, that's 4, right? So this first term right here, this is going to be just 4 root x, right? So far, so good? That whole first term reduces to 4 root x. And then I'm going to have minus 8 root x and then plus 8, right? So minus 8 root x plus 8. Okay, so let's see here. So that means that f prime of x, if I simplify this, what is that? Minus 4 root x plus 8, and then all over x squared. Okay, so that's the first derivative. So that's not terrible, right? Not a terrible first derivative to work with. So what are the critical points? So if I set minus 4 root x plus 8 equal to 0, let's see here. So what would I get? I would have 4 root x equals to 8. So root x equals to 2. So x is what? Mm-mm. 4, yeah, right? You square both sides to solve for x. Yes or no? Yeah, okay. Okay. What about where the derivative does not exist? So this is where the derivative equals to 0, right? So this is a critical point. Where does the derivative equal to 0? Okay, so would I write that down also as a critical point? You don't. You don't write it down. You can, but you don't. Why not? It's not in the domain, right? So the domain is x is greater than 0. So, I mean, it wouldn't hurt that bad if you wrote it down because it's at the endpoint, basically. But I would probably suggest not putting it down just because it could lead you to, other mistakes. Like maybe you might try testing to the left of 0 and then maybe confuse yourself, right? So, when you find the critical points, it's a good idea to go back. Just look at the domain. So is it in the domain or not? So 4 is, so that's okay. So this is fine. But 0 isn't, so don't even worry about it. Yeah? Okay, so now we do our number line business, right? So we have 4 here. So I would probably do this. Let me see here. Okay, so I'm going to put an open parentheses and sorry, not a 4, a 0. So this is my endpoint. 0, and then it's open because I can't actually plug in 0. So what would be some good test points? 3, 5. Okay, 3 and 5. Okay. And where am I going to plug these into? First derivative. 3 and 5. Okay. So actually, I'm going to change them. I don't like 3 and 5. What is it? 1 and 9 are better, right? Why? Because we're going to have to get the square root of it, and getting the square root of 1 and 9 is much nicer than 3 and 5. So, okay, so we have minus 4 plus 8, which is positive, right? Which means my function's increasing. And then we have minus 4 times 3 plus 8, which is negative. So that means that it's going to be decreasing. So what's the interval of increase? 0 and 4, increasing, and then decreasing 4 to infinity. Yep. What is it? Right. I left it out. Exactly. I left it out because it's always positive. Yep. And then do I have any local extrema? Yeah. I do, right? I have a local max. And where is it? It's at x equals 4, y equals to, what is that? 2, right? Where do I get 2 from? Plug 4 into the original, right? So this is 8 times square root of 4 minus 1 divided by 4. That's 2. That's where that 2 comes from. Yeah? Okay. Do I have everything I need? No. Still have to do the second derivative. Okay. So off we go then. So minus 4 root x plus 8 over x squared. This was the first derivative, right? So then the second derivative, so what would that be? Derivative of the top. Minus 4 times 1 over 2 root x. So minus 2 over root x. So that times x squared, right? So derivative of the top times the bottom. And then minus derivative of the bottom times the top. All divided by x to the fourth. So we need to do a little bit more simplifying here. But it's not terrible. If I distribute 2x times minus 4 root x, so what is that going to be? That's going to be plus 8. Let's see. Is it okay if I just write it x to the 3 halves? Yeah, because it's x to the 1 times x to the 1 half. That's x to the 3 halves. And then minus 16x. Right? Okay. And then what do I get from simplifying this first term? That's going to be minus 2 what? So x squared divided by root x. So it's x squared divided by x to the 1 half, which is x to the 3 halves, right? Right? You subtract 2 minus half. Okay, so then if you simplify this, you're going to end up with 6. Well, that's fine. I'll do it in 2 steps. So 6x to the 3 halves, right? Minus 16x over x to the 4th. Okay. But this we actually can simplify it a little bit, right? So if I factor out an x, you would get 6 root x minus 16 over x to the 4th. And so then this x cancels with one of these. And so finally in the end, you have 6 root x minus 16 over x to the 3rd. All right, so it's pretty easy to make a mistake in there, right? A lot of little steps. So now what do we do? Not yet. Find the pips, right? Okay. So how do I find the pips? Where it equals to 0 and where it does not exist, right? Where does it not exist? 0. Do I write it down as a pip? No. It's not in the domain. That's right. Okay, so set 6 root x minus 16 equals to 0. So I get square root of x equals to 16 over 6, which is 8/3, right? So what is x equal to? 64 ninths. Okay. Is that in my domain? Yes, it is, right? Okay, good. So now let's see here. So let's do our number line. So 64 over 9. What would be some good test points? 9 and 4. So 9 would be good, right? And then 4 is, 4 is good. 1 is better, yeah. Let's do 1. What about 0? 0 is no good. Okay. All right. So plug it into the second derivative. So second derivative of 1 is minus 10, right? So that means it's going to be concave down, right? And if I plug in 9, what do I get? 18 minus 16, which is 2, right? So that means it's going to be concave up. So I have an inflection point at 64/9, and then what's the y value? So that's not as nice, right? Oh.
1.875.
Can't be using decimals. What is it as a fraction?
$15.8.
15/8. Oh, Desmos doesn't even do it. Okay. 15/8. Okay. Leave. Let's see. And then concave up on the interval between 64/9 and where does it stop being concave up? Infinity. Good. And then what about concave down?
0 to 64/9.
Yep. All right, so there it is.
So it's always
All our info.
It's always the local max lanes and inflection points where we plug them back into the original equation to find their points on the
Right, because there you're looking for the y value, yeah. Yep. Okay, so questions before we sketch. No? We're okay?
We're good.
All right, let's do it. Let's do it. So we have 8 square root of x minus 1 divided by x, right? So here's 0. So we said that there's nothing over here, right? So I'm not going to do anything over there. So what's my local extrema again? 4, 2. I have a local max. Okay. So then it was increasing and then decreasing, right? The other thing is we have a vertical asymptote at 0, right? And then what's the other thing?
Horizontal asymptote.
We also have a horizontal asymptote at 0. Okay. So, all right, so good to know there. Let's see, what else? My inflection point, where was it again? 64/9, which is about what?
7.
7-ish. So, right about there. 64/9, and what's the y value? So, below 2, right? A little bit less than 2. So this is inflection point. Okay, so it was concave. So from 64/9 to infinity, it was concave up. And then from 0 to 64/9, it was concave down, right? Okay, so now let's see. Is that enough to draw a picture? Can I do it? So here I have a question. Is it going, at the vertical asymptote, is it going up like this or down like that? Is it going to positive infinity or negative infinity? And how can you use the information that you have to figure it out?
Positive. Here from 0. Yeah.
Wait, what did you guys said? Positive infinity?
Can't cross 0.
Okay.
You cross the 1/2.
Cross 0. It just has to stay.
Boy, you have to use information that you have or find out other information. So the way that we used to do it when we went over limits and all that jazz is we would do this, right? So of course you can do this, and if you're unsure, you probably should do this. So remember, what do? You plug in 0, right? What do you get? You get a constant over 0. What does that mean? Infinity or negative infinity. So then what do? You plug in a number close, right? So like 0.1, let's say. If I do that, what would I get? A positive or a negative number? You get a negative number. So it's not going to positive infinity. It's going to negative infinity. Now, how could I have known that? So you actually don't really need to do this. I mean, it's not a bad idea, but you don't actually need to. You have enough information to know that it's going to go to negative infinity. What piece of information is critical there? It's increasing, right? So the fact that it from 0 to 4, you know it's increasing. Well, is that increasing? No. Definitely not, right? That's decreasing. So if you already know it's increasing, it absolutely has to look like that, right? Has to be going to minus infinity. Does that make sense? Okay. All right. So, and if you want to be even more specific, you could find the intercepts, right? This is a pretty easy one. You could find that it's equal to 1 there. Because if you plug in 1, you get 0, right? So we didn't do that, but okay. So it's increasing here, concave down, down, down. What changes there? It starts decreasing, right? And then at this point, what happens? But it's still decreasing, right? But now it's concave up. Now, here, well, what's going to happen? Well, you could go like this, right? Now, is it possible for it to go down and then back up like that? It's not possible. No. It's not possible because if it did this, going down and up again, what would we have found when we did all of our steps? Well, we would have found an inflection point. We would have found another, a local minimum, right? Right? So because so the critical points and the inflection points, that's everything that the graph has. So there's only one possible thing that could be going on here. It absolutely has to go like this, because you already found everything about the function, right? Does that make sense? Okay. Did you guys try putting it on Desmos? Do you guys think we did it right?
Yeah.
Good. We don't make mistakes. So there it is. So there's the max right there, right? 4, 2. And then the inflection point is in there somewhere. And then horizontal asymptote at 0. Okay. Have a wonderful day. Wonderful night.